I would like to announce the last but not least presentation we have today from the last conceptual block. And it's coming from Turkey. We will have presented how Bizeolcat innovative catalysts were adapted to pilot scale reactor and obtained results at pilot scale reactor system compared to performance at lab scale. We have connected already Dr. Serdar Çelebi and Dr. Açıksarı, affiliated with the Turkish petroleum refineries, TÜPRAS, and the Bizeolcat project. Welcome.
Hello.
We are glad to see you both, and a few words for our last researchers who are going to present their results today. Dr. Serdar Çelebi was awarded a PhD degree by Eindhoven University of Technology, and his main research areas cover reaction engineering, hydrocarbon fuel solvents, material synthesis, and electrochemistry. He has been working for over 11 years in the Turkish Petroleum Refineries Corporation, and also leading an experimental research team of 10 researchers. He has been involved in national and international projects at different TRL levels. And Dr. Açıksarı, who holds a PhD in material science and engineering from Eskişehir, I hope I'm going to make it, Eskişehir Technical University in Turkey. He is working as the technical lead of material division at the Turkish Petroleum Refineries Research and Developing Center. Has over 10 years of experience developing novel and innovative materials at different TRL levels, from laboratory to pilot scale production. Also participated in conducting international and national projects, from his role as a researcher to project coordinator. I'm going to pass the voice to you to your presentation entitled Scaling Innovative Bizeolcat Catalysts and Reaction Tests to Reach TRL 5.
Thank you very much, Veronica, for your kind introduction. Okay, hello everyone, good afternoon. Thank you very much for inviting us to show our results in the framework of Bizeolcat project. And we will talk about the scaling innovative Bizeolcat catalyst for the reaction test to reach the TRL5 level together with Serdar Çelebi. Our presentation is divided into two parts, and I will start with the some brief introduction about the Bizeolcat project and catalyst scaling up activities. Then Serdar Çelebi will continue with the pilot scale reactor system and the PDH and the propan aromatization reaction performance results at the pilot scale, and we will conclude our presentation with some important findings. So here is the main objective of the Bizeolcat project, to obtain the light olefins and aromatics by using light hydrocarbons, by innovative catalyst synthesis methodology and novel reactor design and processing, demonstrating improvements in front of existing industrial process. So you can see on the right side, here is the our Bizeolcat partners from development stage to validation stage. As a TÜPRAS, we are on the demonstration and the scaling up activities of the project. So it is the work package 4, demonstration and scaling up activities. The leader was the National Institute of Chemistry in Slovenia, NIC, and we have two tasks in this work package. One of them is related to catalyst development, catalyst scaling up, not development. Another one is the reaction test at the pilot scale. So in task 4.4, TÜPRAS extrudates powder supports that was defined in the development stage of the project and shaped them as a pellet form by extrusion process in order to test it in pilot scale reactor for propan dehydrogenation, butane dehydrogenation, and propan aromatization reactions. In task 4.5, TÜPRAS performs industrial environment pilot scale fixed bed reactor test for PDH, BDH, and propan aromatization. For the reaction side, today we will discuss and give the results on propan dehydrogenation and propan aromatization reaction. So final catalyst for PDH and BDH was defined in the work package 2 by the technology developers, Eurocats and CNRS. This is the lithium doped gamma alumina deposit by the platinum and tin. This is the ratio tin over platinum is 0.7 and lithium is nearly 0.5 by weight percent. The catalyst was prepared via novel process. It's called the surface organometallic approach that was developed by CNRS and the Eurocat. And to reach the TRL 5 level for catalyst scale-up, activated alumina catalyst support. This is the gamma alumina, which is the 0.7 millimeter in diameter, and 3.3 millimeter in length, have been produced with the Secret type classical extrusion process. Our first step is the preparation of the paste. This contains Boehmite particles, and we change solid loading and the gelation ratio with a nitric acid concentration in order to increase the mechanical strength and increase to reach the maximum extrusion yield. And then this paste with the optimal properties and viscosity, extrusion then extrusion process continued with a die diameter of 1 millimeter and breaking up of extrudate into small in length. And then this catalyst was dried at a 90 centigrade degree for overnight. And then heat treatment was applied in order to produce gamma phase at nearly the 600 centigrade degree for 5 hours to optimize, maximize specific surface area and optimize pore size distribution and pore volume. Here is the catalyst support production equipment that was installed in our R&D center. This is the Caliber brand extruder 3-in-1 machine. We are making, in this machine, we are preparing paste. We can make extrusion, and we can also use siphonizer units attached here to produce a spherical material. This is another mixing in order to increase the capacity, and this is the granulation equipment and also mixing equipment in order to produce kilogram scale material. In this table, you can see some critical properties of our support. This is the high purity gamma alumina with a very low diameter, and crashing strength is 45 Newton per millimeter. That is enough for the propan dehydrogenation reaction. This is the surface area is higher than the 200 meters square per gram. So we can say that industrial grade industrial grade gamma alumina support were produced to be used for PDH and BDH for the TRL 5 level. You can see in the graph, this was taken from the different batches. This is the NH ammonium TPD analysis. We obtained the same total acid site, and we have also the same BET nitrogen absorption and desorption graph, and also the same pore size with the different sizes. So our production are very robust in terms of the material properties. You can see on the left side, this was developed by our partner, CNRS, in order to produce 1 kilogram final catalyst for the impregnation of platinum tin. The preparation of the catalyst, platinum tin on the lithium doped gamma alumina from 2 grams to 1.1 kilogram has been successfully completed. And when you look at the ICP results, we obtained the very good results when compared to laboratory and the pilot scale production. So when we look at the reaction performance, we can say that similar catalytic performance was observed for catalyst platinum tin supported on TÜPRAS lithium doped gamma alumina prepared on large scale and the small scale with the same reaction conditions. So you can see the microstructure analysis of final PDH catalyst. This is the cross-sectional analysis of our catalyst. We can see the outer side of the catalyst and the inner side of the catalyst. Okay, we are using this is the typical distribution of the metal on the support. We have a rich layer of platinum tin on the top of the catalyst, and when we go to the center of the catalyst, the platinum tin concentration decreases. But when we compare with the commercial catalyst, the distribution is we can say that distribution is very good, and the results are very similar with the ICP and the SEM EDX analysis. So I will move to another reaction. This is called the propan aromatization reaction. The final catalyst for this reaction was defined by technology developer. Here is the University of Oslo and CNRS was work on it. And gallium dope, the gallium modified mesozeolite with almost nearly 1% by weight of gallium, and the silica alumina ratio is 40 by mole. The catalysts were synthesized by treating of commercial zeolite with sodium hydroxide solution to introduce mesoporosity. This is for the support. The final catalyst was prepared with the same technique by the surface organometallic approach. This is also the novel technology was developed by CNRS. To reach the TRL 5 level, we used the same approach, but this is a little bit different because we used the bentonite, and we changed the bentonite ratio and the solid loading in this composition in order to increase mechanical strength, reach the maximum yield and the maximum mesozeolite loading to improve the catalytic activity. And here is on the right side, you can see the powder material performance here for the reaction. To reach this performance, we shaped the mesozeolite with a different silica-based binder. One of them was prepared was colloidal silica, another one was prepared by the mesozeolite. When we look at the reaction performance, it was very, very low when compared with the bare catalyst in a powder form. So low acid-dense selectivity was obtained by the shape support for the mesozeolite with bentonite or colloidal silica. So we had to improve this performance by reducing the inorganic binder and also reducing the calcination temperature after shaping. So this reason, it can be explained by the reduction of acidic proton when seen at the 4 ppm in the solid state NMR results. When we put some inorganic binders, this peak disappeared. When we increase the calcination temperature up to 700 centigrade degree, we also we have an acidic proton peak in the spectroscopy, but the intensity of the peak is lower. So the calcination at 7 centigrade degree to complete the bentonite formation into the mixed oxide is undesirable due to the decrease of acidic proton, and it reduced the catalytic activity. So we decided to reduce both calcination temperature and inorganic binder in order to increase the reaction performance. When you look at the right side of the propan conversion and the mass selectivity in the BTX, we have, lower than the powder, but we have a very promising results on the propan aromatization. You can see on the right side, this is the material properties, and this is the picture of our catalyst. For the final PA shaped catalyst, the selectivity towards aromatic reached the 55% as gallium loaded mesozeolite powder has BTX selectivity for 65. The conversion was calculated as 65%. The powder was around 80. So this is, we have reached the, let's say, the similar results, promising results, but we reached the higher results after modifying our extrusion formulation. Then my colleague Serdar will continue with the pilot scale reactor system.
Thank you, Cem. Serdar is speaking from Turkish Petroleum Refineries Corporation. I will continue with the task 4.5, the pilot scale experiments and our reactor system. Our pilot scale reactor system is called as X2L, enables us to make the dehydrogenation, dehydroaromatization, Fischer-Tropsch reforming, hydroformylation, and hydroprocessing type of reactions. But of course, this is a custom-made system and specially designed for Bizeolcat project. This system has its own chiller system. Also, we have the water condenser at the outlet of the reactor. And we are collecting the liquids in our collection vessel, and this system is can be operated at this kind of high temperatures. And the system is also coupled with an inline gas chromatograph, micro GC, and we are measuring the inlet composition and the outlet composition of the products. The micro GC is coupled with 3 different columns. One of them is the mole sieve column, the second one is alumina column, and the Plateau column. All of these 3 columns are also capable of measuring different kind of molecules, including the hydrocarbon C1 to C6, and also nitrogen, oxygen, hydrogen, carbon monoxide, and carbon dioxide. And how we load the reactor. This reactor system allows us to use different diameters reactor tubes, starting from 1/2 inch, 1 inch, and 1.5 inch. And we used 1.5 inch reactor diameter in propane dehydrogenation and also propane aromatization reactions. We are loading the catalyst diluted with the silicon carbides just in the middle of the reactor tube, and we are controlling the reactor externally, and we are measuring the reactor temperatures inside from 3 different locations. And we are very good on the control of the catalyst bed temperature, but of course the external temperatures are almost 50-60 degrees higher than the internal temperatures because of the endothermic nature of the reaction. And when we start, let's start with the propane dehydrogenation reaction performance at pilot scale. We did a lot of different type of experiments at lower scale, around 12.5 gram. And all of these reactions are completely repeatable. We controlled the reaction temperature outside 590 degrees, and internal temperature was around 530 degrees Celsius. And we maintained the weight hourly space velocity around 5.7. And we also feed hydrogen in order to get rid of the coke formation during the course of the reaction. Here you see 11 hours of operation. It's a continuous operation, by the way, almost 36 hours of complete operation, including the reduction of the catalyst. And we maintained around 95% selectivity at the end of around 10 hours of operation. And in this reaction, we obtained also C2s, ethane and ethylene, and also methane around 2.6%. And the reaction started with 22% in conversion of propane and end up with around 19% at the end of 10 hours. And we increased the catalyst capacity for the next round. It is right now increased to 10-fold to 125 gram in the fixed bed reactor, and we used, of course, a 1.5 inch of reactor tube in the diameter. The conditions are almost the same as before, and we started with a higher conversion and just dropped again to 20% in 9 hours, and we maintained the propylene selectivity around 93%, and the C2 and methane is almost the same like in the previous one as the selectivity. When we come to the propane aromatization reactions, we actually surprised a lot when we get the results, because working with such a kind of a reaction in a pilot scale is very, very difficult because of the aromatics, especially the benzene that you have obtained as a product. And you have to be very careful on handling of this kind of products. Our external reaction temperature is around 625 degrees Celsius, and the internal temperature was 580 degrees. And the amount of catalyst is 42 grams. And we used this reaction actually is validated in the lab with argon, not with nitrogen. But of course, it's very difficult to find argon in an industrial environment. Therefore, we first started with the nitrogen in order to see what is the effect of nitrogen in this reaction at pilot scale. Of course, we didn't obtain almost nothing, just a couple of droplets of liquid product observed in the chiller section of the collection vessel. And therefore, we decided to, of course, go to the argon flow with the same WHSV values. We try to fix that value and the propane flow, and accordingly change the catalyst amount in order to fix these values. And the propane aromatization reaction performance with the argon flow at the flow capacities tabulated in this table. We obtained liquids in each hour, as you see in this picture, and the product color is dark brown. And when during the course of the reaction, after the 5 hours, 6 hours, the color is going to be transparent. And we understand that the benzene concentration in the initial phase of the reaction is higher than the final phase of the reactions. And we of course try to validate these results with the detailed hydrocarbon analysis. And we repeated reaction once again. And here you see the products. We obtained the same color change during the reaction. And you see that during the course of the reaction in 10 hours, the total aromatic mass concentration was always above 95%. All of these liquids are almost completely aromatic. And here, when we look at in detail hydrocarbon analysis, the C6 concentration here, you see in the orange one, is decreasing with time, and C7 concentration is also decreasing, and C8 concentration and also the hydrocarbons higher than the C8 was also increasing. When we look at the more details on that, the distribution of aromatics, especially the orthoxylene and metaxylene and paraxylene concentrations here are increasing, and the C10 concentrations are also increasing. The xylene, here you see that metaxylene, thermodynamically the most stable one, is dominant among the other xylenes. And we have obtained a steady state behavior at 8 hours, and concentrations are getting stable after this point. And when we look at in detail of this C9 hydrocarbons and C10 hydrocarbons, we get this ethyl toluenes and 3-methyl benzenes mostly in the liquids, and also we have some propyl toluenes in C10 fraction. Therefore, propane aromatization reaction is shown in pilot scale. We collected this liquid, by the way, by chilling the outlet of the reactor at -10 degrees, because you cannot condensate this product at room temperature. You will get nothing in the collection vessel. You have to decrease that temperature below -degrees in order to condensate all of the outlet stream, especially in that dilutant stream, because 95% argon is just given in 5%, 5% propane is given in 95% argon. And when we look at the spent catalyst, the thermogrametric analysis, we can regenerate the catalyst, especially. The spent catalyst is seen to be cooked during the course of the reaction, and especially this, you see here the circle, the coke combustion starts around 250, 300 degrees Celsius, and the catalyst can be regenerated from the coke. The coke formation is a major problem, of course, in the reaction. And as a conclusion, the propane dehydrogenation, propane aromatization catalyst scale-up has been completed in collaboration with the technology developers. And here you see that the best performing propane dehydrogenation catalyst and its performance, when we consider that one, that the catalyst support was shaped via extrusion process, starting from the aluminum oxyhydroxide particles. And we obtained almost thermodynamical conversion around 20% in ton hours, and selectivity was around 94–95%. And the best performing PA catalyst and its performance was around 1% gallium loaded mesozoolite. And of course, the conversions are really so low, but we obtained some kind of reformate in the refineries. We call it reformate from propane. And it was quite surprising for almost all of the refinery people in TÜPRAS, because normally we produce such aromatic product from heavy naphtha, not of course propane. And of course, this kind of reactions are really so important for the utilization of propane rather than using it for LPG. Therefore, it's very important for refinery integration in the future. We did pilot scale tests. These were very difficult indeed. 125 gram up to 125 gram of catalyst is used in these tests. And we run these reactions around 10 hours. And we obtained the results, that in the propane aromatization reaction, argon should be must be used in the reaction rather than nitrogen. And higher propane concentrations did not allow us to get any liquid, of course, in the reaction as well. This is our presentation. Thank you very much for your attention. If you have any questions, I'd like to be answered with Cem.
Thank you, Dr. Çelebi and Dr. Açıksarı. We do have a few questions for you online. Before that, we have a question from our room.
Thank you for your presentation. It was very interesting because you prepared the materials but also evaluated their performance. Have you tested the spent catalyst to see if there is any change in the morphological or structural characteristics of the catalyst?
Actually, we didn't. We only checked the carbon deposits on the catalyst, but we didn't check the formation or restructuring of the gallium particles on the catalyst. But of course, after the initial phase of the reaction, the catalyst itself is changing. It's not stable, we believe.
Okay. And another question is, do you have facilities to do wash coating, let's say to have a monolith and then to wash coat the catalyst on the surface of this monolith?
We don't have that kind of equipments in our laboratories, but we are just using that, extrudates in our facilities. Yeah.
Okay. Thank you. Thank you.
Thank you.
Thank you for the question. The upcoming question from the room will be asked.
Good afternoon, gentlemen. Can you hear me?
Yeah.
Thank you for your interesting presentation. I was interested to hear your surprise find that you're also producing reformate from your propane process. Reformate, as you explained, is a very important stream in a refinery. Are you planning to use and optimize this technology to produce more of this particular stream?
Actually, here the idea is, refineries are trying to convert this heavy naphtha fraction to aromatics. And the propane conversion, propane to aromatics, is really very, very, let's say, feasible, because propane, finally, the propane price is much lower than the price that you are using. And I mean, heavy naphtha, it's much more expensive. When you find a way to convert propane directly to benzene, toluenes, really will hit the refinery business. But of course, the reaction is not easy. There is a lot of problems. There are a lot of problems, like, you know, you have to use argon. You are in a very low concentrations, and the catalyst is not stable. Therefore, I expect that it will make a very big impact on refinery processing.
Okay, thank you. Good luck with your further experiments.
Thank you.
Thank you for your attention to our questions. Our online open question for you would be, why does the benzene concentration decrease with time?
Yeah, that's indeed a very good question, because you see, when you look at the concentration differences of the aromatics, benzene, toluene, the reaction itself is not, of course, only, you know, it's not only an aromatization reaction. We understand it's also the propane dehydrogenation happening at the same time. Therefore, you are getting propylene somehow in the reaction. And we believe that this propylene is somehow alkylated with the benzenes, and you are getting at the end much more stable C9 fractions rather than benzene at the end. But I don't know that how this mechanism is really just happening, because this is the first time that we really saw such a change in a catalyst. When you look at the laboratory work, you are ending up with the benzene mostly. But at this kind of, you know, higher flow rates and the higher higher, you know, propane amounts and the long reaction runs, then you are realizing such a difference. And we understand that this might be because of the propylene effect in the products.
Thank you for answering our question. And I think I have the last question for both of you this evening, most of the evening. Do you think that PD weight can be decreased more for propane dehydrogenation reaction?
Excuse me, could you repeat the question
Of course.
again, please?
Do you think that PT weight can be decreased more for propane dehydrogenation reaction?
I think so, because in industry we are using the platinum tin catalyst with a platinum ratio is around 0.5% by weight, or maybe lower than of this ratio. When we control the platinum tin atomic ratio in order to produce the platinum tin nano particles, I mean the alloy, it can be reduced. When we reduce the platinum ratio, and it will be more feasible in the on the industrial point of view.
Thank you both. Thank you for explaining. These were our set of questions for the topic, and applause for both.
Thank you very much.